Okay, so this is page 2 of your notes. We're going to solve for some frequency and wavelength expressions. Again, just reminding you that c equals the speed of light, and the speed of light is always 3 times 10 to the 8th meters per second. Lambda represents wavelength, and frequency represents the speed at which a wave passes per unit of time, which is going to be in seconds. So, if c equals 3 times 10 to the 8th meters per second, and this answer never changes, that means our lambda, our wavelength, must be in meters. And our frequency, our nu, must be per second. So every calculation we do, we need to get wavelength in meters, and we need to get frequency in seconds if it's not already put there. So for the first question, it says, what is the frequency of light with a wavelength of 550 nanometers? So here, right off the bat, we're given nanometers, not meters. So if we're given 550 nanometers, we just need to convert this using dimensional analysis to meters. So for every 1 nanometer, it's 1 times 10 to the negative 9th meters. Nanometers cancel. And you get 5.50 times 10 to the negative 7th meters. So now what? It's asking for the frequency, so we don't know nu. We know c, because it's always the same, 3 times 10 to the 8th meters per second. We now know wavelength, 5.50 times 10 to the negative 7th meters. We just need to find the variable nu, which represents frequency. So, to get nu by itself, we just divide each side by 5.50 times 10 to the negative 7th meters. 5.50 times 10 to the negative 7th meters. Your units of meters will cancel. So now all you have left over is 1 over s. And 1 over s represents frequency. It was one of the units that we talked about. So, frequency equals 5.45 times 10 to the 14th 1 over s, or you can write it as hertz, or you can write it as seconds to the negative 1. I like to use seconds to the negative 1 in most of my answer keys, so if you see that, that's the same thing as saying 1 over s. Alright, next question. Number 2. What type of light has a wavelength of 5 times 10 to the negative 4th meters, 2.4 times 10 to the negative 8th meters, and 12 millimeters? Okay, so we need to look up our electromagnetic spectrum. So in this electromagnetic spectrum that I give you, unfortunately, a lot of them are represented in nanometers because it's really, really small between crest to crest. But over here, it's represented in meters. So the first one was 5.0 times 10 to the negative 4th. Okay. So here's 100 meters. That's too large. 1 meter. 1 times 10 to the negative 2nd meters, because centi is negative 2. 1 times 10 to the negative 4th meters, because this is to the negative 2nd, and it's centimeters. So this is 1 times 10 to the negative 4th. So the first one, A, is infrared, IR for short. For letter B, it asks 2.4 times 10 to the negative 8 meters. So 2.4 times 10 to the negative 8. Well, nano means 10 to the negative 9th. And 10 to the negative 9th, and if you add 1 0 to the end, it's like you're moving the decimal in the opposite direction. So this is the same thing as saying 1 times 10 to the negative 8th meters, which is right here. So it says 2.4, so it must be slightly in this side, and that is your ultraviolet or UV rays, what you get in tanning beds or from the sun. And the last one is 12 millimeters. So 12 millimeters is 1.2 times 10 to the negative 3rd. So it's somewhere between here. So let's just say they're radio waves, probably. If it's 0.1 centimeter, then it's probably right here, and we're looking at radio waves here. So you can always use the wavelength in the electromagnetic spectrum to see what type of radiation you're dealing with in a problem. Okay. Number 3. Says an ultraviolet light is used to kill bacteria, and that's true. It has a frequency of 1.2 times 10 to the 15th seconds, so per second, seconds to negative 1. So it says find the wavelength. Okay, let me get this out of the way so you don't get confused by it. So if we're trying to find the wavelength of this UV wave that has a frequency of 1.2 times 10 to the 15th seconds to negative first power, we just use this equation again. C equals lambda nu. So C is always, always, always 3 times 10 to the 8th meters per second. Lambda represents wavelength, and I don't know my wavelength here, so I'm just going to leave it. And then frequency is represented by nu, and it needs to be in terms of seconds, or seconds to the negative 1 power. And it is here, so we don't have to change anything like the last problem. So now we just need to get lambda all by itself to solve. So divide each side by 1.2 times 10 to the 15th seconds to negative 1. 1.2 times 10 to the 15th seconds to negative 1. And here is where the units get kind of confusing. If you originally have seconds to the negative 1, meaning 1 over seconds, and then you put it in the denominator, all of a sudden you're flipping this back over to seconds to the negative 1. So what you have in your numerator is 1 over s divided by s over 1. So these guys will cancel. And what you have left over is meters. So I got lambda equals 2.5 times 10 to the negative 7th meters. And then I went ahead and changed it to nanometers because most of your wavelengths are expressed in nanometers because they are so small. Okay, let's see what number 4 is. Okay, so number 4 says an X-ray has a wavelength of 1.54 times 10 to the negative 10th meters. Find the frequency of this light. I think you can do this on your own. Go ahead and pause the video and then I will reveal the answer. Okay, so in this answer, they already gave you wavelength in meters, so that's perfect. So I plugged that in for lambda, our wavelength. They did not give you frequency, but we always know that C equals 3 times 10 to the 8th meters per second. So I got my frequency to be 1.95 times 10 to the 18th seconds to the negative 1 power. Hopefully you got that too. All right. Go ahead and try number 5 on your own, and then I'll reveal the answer. Okay, so it says a visible wavelength has a frequency of 7.5 times 10. This should be 7.5 times 10 to the positive 14th, 1 over seconds. Find the wavelength in nanometers. Okay, so they're telling us we got to find it in nanometers and determine the color of the light. So if we use C equals lambda nu, C is always 3 times 10 to the 8th meters per second. And so because it's asking us to find the wavelength in nanometers, even though when we set up our problem, this is in meters, we can't solve for nanometers until afterwards because our speed of light constant is always in meters per second. So we're first going to find wavelength in meters and then we'll convert it to nanometers. And our frequency is 7.5 times 10 to the 14th, 1 over s. So, to find lambda, you just divide each side by 7.5 times 10 to the 14th, 1 over s. Your s's will cancel. And now you'll get lambda equals, let's see, what did I get? 4 times 10 to the negative 7th meters. So, because they said they want it in nanometers, we know there is 1 times 10 to the negative 9th meters in 1 nanometer. We did our dimensional analysis. And so our answer will be 400 nanometers. And that's it.